Hey everybody, this is the first video for the 4.5 notes for AP Calculus, and in the video we're going to take a look at tangent line approximations and linearization, and within here we'll also look at secant line approximations. So we have a question that says, consider the graph shown. How could we estimate the value of f of x at values close to x equals 1? So one way to estimate values of x at values close to 1 would be to draw a tangent line to the graph at x equals 1. So if we were to, whoops, it's not letting me draw. If we were to draw a line tangent to the curve at x equals 1, we would be able to use that line to approximate values of the curve that are close to 1. So it could be a point here, it could be a point over here. And that's essentially what we're going to be doing in the video. So we have some steps here for performing a tangent line approximation. Step 1 says to write the equation of the tangent line at the given x value. We're going to use the derivative to find the slope. And that's just the connection. The derivative at a point is equal to the slope of the tangent line at that point. We're then going to evaluate the tangent line to get our approximation. And then the next thing we have to do is determine the concavity of the function at the tangent line. And then for step 4, it says if the function is concave up at the point, the tangent line is going to provide an over approximation. And if the function is concave down at the point, the tangent line is going to provide an under approximation. And those are actually backwards. If a function is concave up, then a tangent line will provide an under approximation. And if the function is concave down, it will be an over approximation. And we'll talk a little bit more about that as we get into the video. So let's take a look at example 1. It says, given the function g of x, which is equal to 4x squared minus 5x at x equals 2, we want to use a tangent line to approximate the value of g of 1.9. Then we're asked, will this be an underestimation or overestimation? And we need to justify our conclusion using calculus. So how we're going to approach this is we need to have an equation of the tangent line. So we need to take the derivative of g, which in this case is simply going to be 8x minus 5. Then what we need to do is calculate the slope of the tangent line at 2, which is basically g prime of 2. So we get 8 times 2 minus 5. That's 16 minus 5, which is 11. So the slope of our tangent line is 11. That's g prime of 2, guys, but that is also the slope of our tangent line, which is going to be important. Now the other thing we need to write the equation of a line is a point. We're given the x-coordinate, but we do still need to find the y-coordinate. So we need to calculate g of 2, which is 4 times 2 squared minus 5 times 2. 2 squared is 4. 4 times 4 is 16. So this is 16 minus 10, which is 6. So g of 2 is 6. All right, so we've done some calculations. Now we're going to write the equation of our tangent line. And you can really put it in any form you want, but it seems like HK form seems to be the preferred method. So we're going to go ahead and write our tangent line as y equals our slope, which is 11, x minus 2, and then plus 6. So that right there represents the equation of the tangent line. Now, we want to use that equation to approximate the value of the function at 1.9. So the way we're going to do that is we're going to take 1.9 right here and substitute it in for x. So when we do that, we're basically doing y of 1.9, which is 11 times 1.9 minus 2 plus 6. And if you wanted to, you could plug that into your calculator. So I'm just going to pull that up. So we have 11. Let's see if this is going to let me work here. All right, 11 times 1.9 minus 2. And then we had plus 6. And the plus didn't show up. So plus 6. All right, and what we end up with is 4.9. So if we go back, we get approximately 4.9. So that value is our tangent line approximation. Now, what we need to do is we need to determine if that's an over or under approximation. And what we do is we need to determine the concavity of the function. So you hopefully you remember from earlier lessons that the concavity is determined by the second derivative. So we are going to take the second derivative of our function g, which is simply the derivative of the first derivative, which is 8. All right. Now, because g double prime, or the second derivative, is greater than 0, that means that our function is concave up. All right, and in this case, it's always concave up, which should make sense because we're dealing with a positive quadratic function. Now, in order to decide if this is an over or under approximation, think about it like this. If this is my curve, and I have the tangent line, let's say at this point, so that's the tangent line at 2. Your tangent line is going to look like this. And if this is 2, then 1.9 might be approximately here. So the value that we're getting is this particular point right here, which you can see is below the curve, which makes this an under approximation. So when our function, when our function is concave up, our tangent line approximation will be an underestimate or under approximation. And it does say to justify our conclusion using calculus. So we could say that g double prime of 2 is greater than 0. So g of x, g of x is concave up at x equals 2. And the tangent line is below the curve. Making it an under approximation. Or underestimate. And guys, that's how a tangent line approximation is going to work. You write the equation of the tangent line at a given point, you substitute the value for x, and then you use the second derivative to determine concavity. If the function is concave up, then you are going to have an underestimation with the tangent line approximation. If the function is concave down, then it's going to be an over approximation with a tangent line approximation. All right, guys, that's going to be it for part 1 of the video. In part 2, we will take a look at how we can take and do a secant line approximation.